So first I want to ask, do you have any questions about anything that was during the previous times? Uh, okay, so today I wanted to talk more about the green functions. A reminder. Uh, Last time we found the green function of the heat equation. We were solving this equation dt g minus Laplacian g equals to delta of t delta of x, and this green function was by the way, does anyone remember the formula? Maybe some essential part, and then we can think about normalization coefficient. Mm-hmm. Mm-hmm. Yes. Mm-hmm. And mm-hmm. Mm-hmm. Thanks. Yes. So it is this function, and if we want to solve this equation with some function on the right hand side, so if we want to solve dt u minus Laplacian of u, let me write u of t and x minus Laplacian of u of t and x equals some f of t and x. Then solution can be written, the general solution of this equation can be written as the integral from minus infinity to plus infinity, in all variables actually, dt prime dx prime g of t minus t prime x minus x prime. Actually, the f of t x prime. This works for any equation. But why I'm reminding this? Because now I want to compute the green function of this equation without time derivative. So the question is, so it was for the heat equation. The question is, can we use this somehow to find the green function of Poisson equation? So, namely, we want to solve the equation. We want to write a formula for a solution of such equation without time derivative. Namely, we want to solve this equation, Laplacian of u of t and x, Laplacian u of x equals to some rho of x And we expect that it should be written as u of x some integral in R d dx prime, green function of Laplacian of x minus x prime, rho of x prime. The question is, what is the formula for this green function? So there is, of course, a kind of industrial way to compute this, because we can do precisely the same. We can go to the Fourier representation, invert this Laplacian operator, which will be minus 1 over k squared, and compute the inverse Fourier transform. But actually, we know a solution of a more complicated equation. We know a solution of the heat equation, which has this extra derivative. And I propose to simplify this computation using this using the knowledge of this green function. So, namely, let us try to solve the heat equation with the right hand side independent on time. And we should substitute here a minus rho. dt of u of x equals minus Laplacian of u of x equals to minus rho of minus rho of x. So this vanishes because this function is also time independent. And this suggests that we can just use this formula for this f of t prime x prime time independent. So u of x is given by the integral from minus infinity to plus infinity, integral from minus infinity to plus infinity, dt prime dx prime, so with overall minus sign, g of t minus t prime, x minus x prime. So rho of x prime. We see that the only dependence on t prime is in this green function. So we can conclude that maybe better write solid line here. So we can derive the formula for the green function in this form, in this formula. So for the green function of Laplace operator. On the question to you, what is this formula? So if you compare this and this, what is the formula for G Laplacian? Mm-hmm. Mm-hmm. Yes. Thank you. So dt prime g of t minus t prime x minus x prime. And But now we can use this explicit formula and write that it is actually the integral from minus from 0 to plus infinity, because if this argument becomes negative, it just vanishes. So we have the integral only over the half line. So we can write that g delta of x minus x prime is the integral from 0 to plus infinity of this gain function written explicitly. dt prime, or maybe just dt, it doesn't matter. It's integration variable. So here we have this integral. We see that it is convergent around 0 because this t goes to infinity, and so this exponential goes to 0 very fast, much faster than this factor goes to infinity. And when we go to infinity, this exponential goes to 1 because its argument goes to 0. And now it depends. If d is greater than 2, then this integral is convergent. When d is 1 or 2, it is divergent. But we can perform the analytic continuation d. So we will see this later when we derive some explicit formula for this gain function. Sorry. Here it is a function of difference, of course. So is it clear? Hmm? Because we integrate in t prime from minus infinity to plus infinity, and we can just shift by t. So this integration variable is actually the difference t minus t prime. So I can write it like d t minus t prime. How to write this t minus t prime? Oh no. Okay, I can write it also here. But in any case, this variable changes from 0 to infinity, because if it becomes negative, the integrand vanishes. So, okay, so since it depends on the difference, we can write it as a function just of x. G of x is the integral from 0 to plus infinity dt e to minus x squared over 4t 4 pi t minus delta over 2. So now I want to reduce it to something known, and to do this, we can do the following rescaling. So scaling is, so we choose this argument of the exponential as a new integration variable. So t will be x squared over 4, let us call it y, for example. So this integral is the integral from 0 to plus infinity in dy. Then we should write this Jacobian x squared over 4y squared times e to minus y times 4 pi x squared over 4y to in d over 2. So this cancels. So sorry, minus d over 2. So now let us find the power of absolute value of x. So here it is absolute value of x squared. Here it's absolute value of x to power minus d over to power minus d. So it equals to absolute value of x to d minus 2 times so there is this 1/4, and there is pi to minus d over 2. And here we have some integral which does not depend on anything except for dimension of the space. So like this. And, so, do you have some questions? Yes, thank you. Yes. Yes. So, and do you know the value of this integral? So, yes, of what argument? Actually, d over 2 minus 1. So, because the formula for the gamma function of p is the integral from 0 to plus infinity e to minus y to p minus 1 dp. So it works for p is greater than greater than 0, I think, because otherwise this integral is divergent. But it can be continued analytically using cancellation. But in any case, it is and also if you compute it at integer points, then gamma of, so in general, gamma of n plus 1 or gamma of p plus 1 equals to p gamma of p, and So this way we can compute it for integer points, so namely gamma of n plus 1 equals to n factorial. And also for half integer points, but then we will need to compute gamma of 1/2, which is something like square root of pi over 2, something of this form. But actually, we don't need this explicit values. We can just write that it is something. So let us write it like this: 2 minus d. But maybe, in principle, we can compute it for some small values. 5 minus d over 2 over 4 gamma of d over 2 minus 1. Sorry. There was also this minus sign here, and it should be written everywhere. Sorry. So it should be here, 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 and here, and here. So there is this formula. Let us maybe compute this for d equals to 3. So when d equals to 3, we need this g delta will be minus 1 over absolute value of x. This pi to minus 3 over 2 over 4 gamma function of 1/2. And so this should be computed. It's not very complicated. So let us do it here. So gamma of 1/2 is the integral from 0 to plus infinity e to minus y, y to minus 1/2 dy. Oh, sorry, it is dy. So it is 2 integral from 0 to plus infinity e to minus y. And let us write this as 2d square root of y. Sorry, I wrote this 2 overall. Let's write it this way. So we can just combine this y minus 1/2 and dy into this combination. So this can be written as the integral from minus infinity to plus infinity e to minus some z squared dz, which is equal to square root of pi. Okay, so this gamma of 1/2 is square root of pi, and the answer is minus 1 over 4 pi absolute value of x. So here it is. Are there any questions? So it is some function that decays at infinity. And now let us go to this case d equals 2. Namely, we see that there will be some problem, because namely it will be something d independent. But let us look at this more carefully. Namely, let us formally write that it is not 2, but some 2 plus epsilon. It's also used in physics when people have some divergent integrals. So one way to regularize something is to multiply by some cutoff function, and another way is to change the dimension of the space-time. And in some sense, it's one of the best regularizations. So if you use it here, so what will what will we get? Um, we'll get minus absolute value of x to minus epsilon pi to minus 1 minus epsilon over 2 over 4 gamma of epsilon over 2. And to see what happens with this gamma of epsilon over 2, we need to use this relation that gamma of x plus 1 equals to x gamma of x. It can be checked from the from this integral definition by integration by parts. So we can use this formula in the opposite direction. We can write that gamma of x equals to 1 over x gamma of x plus 1. And when x goes to 0, gamma of x behaves like 1 over x. Gamma of 1, and gamma of 1 is just 1. So this asymptotics, and let us use this asymptotics here. Maybe better to say that it is gamma of 1 plus, let us write this explicitly. So this will be minus 1 over epsilon. And let us write it in the exponential. So 1 over epsilon, 1 over 4 epsilon pi, and the exponential minus epsilon log of absolute value of x minus no, sorry, it's not one space here. So there is this kind of expression, and let us now move to some other blackboard. So which is minus 1 over 4 pi epsilon e to minus epsilon log of value of x plus we can write all this as some constant times epsilon, because this is a logarithm of pi over 2. This is some first term of expansion of this gamma function, which is a Euler constant, but we don't care about this because it is just some constant. Plus, so it is plus epsilon c. And if I now expand it as a series in epsilon, we will get minus 1 over 4 pi epsilon plus, by the way, probably I missed some factor. Namely, it should be 1 over 2 pi epsilon, because there was epsilon over 2. Let's say it was better. That should be 1 over 2 pi epsilon. Plus 2 pi, sorry, 1 over 2 pi logarithm of absolute value of x over c. So now we can write it as some constant plus logarithm of plus 1 over 2 pi logarithm of absolute value of x. And now this constant does not matter, because Laplacian of a constant equals to 0. So so if you take some solution of this Poisson equation shifted by constant, it will still be a solution of this equation. And the only difference with three-dimensional and high-dimensional cases was that in that case this green function decayed at infinity, and so we could say that these possible constants are ruled out by this asymptotic behavior. And this Green function does not decay. It goes to infinity both at 0 and at infinity. So there is no way to fix that constant. So we can say that it should be chosen in some way. So any such Green function will provide us with a solution of this equation. So we can say that some chosen Green function of x is just 1 over 2 pi logarithm of absolute value of x. It hmm? Which so which quality? I'm just expanding this exponential as a series in epsilon, isn't the question? So, and, and, and there is some term that goes to infinity, but it is constant, and there is some term which stays regular, and this is this logarithm of x. So is it fine? And uh, so, so are there any questions? Well, hmm? Hmm? Yes, yes. So it was oh, so I can write it here again because it was for dimension 2 plus epsilon, and then now we took this limit. Uh, but we can also verify this independently. Uh, so So what are we solving? We are solving the equation Poisson of uh, u of x equals to a delta function of x. And so one thing to check is that this logarithm of x is actually cubed by Laplacian, and it can be done in some straightforward way, and we'll actually come to this later. Maybe I can say it right now actually, because so when x is different from 0, uh, we can introduce complex coordinates. So there is z, which is x1 plus ix2, and z bar, which is x1 minus ix2. Uh, so absolute value of x well, x squared equals to z times z bar. And if you want to write a Laplace operator, we need to write derivatives in x1 and x2 in terms of derivatives of derivatives in z and z bar. So um, how to do this? We write that dx1 is some combination of d mm, or maybe better to write in the opposite direction. So let us write that dz is some combination of dx1 plus dx2 dz bar equals to dx1 minus dx2 uh, no, multiplied by something. And the question to the audience. Um, uh, uh, what should we write here? Oh, so no, actually the coefficients are also not like this. Uh, they should be modified. So basically we want this derivative to kill this variable. And to do this, we write here minus I dx2, and here we write plus I dx2. Oh, and the question is, what should we write here? What coefficient? Mm-hmm. Nice. And now if I compute dz bar, dz bar, it will be 1/4 dx1 squared plus dx2 squared. So it will be 1/4 of Laplacian. So always versa Laplacian equals to 4 times dz bar. And now let us act on this logarithm. So Laplacian acting on logarithm of z of absolute value of x equals to Laplacian acting on logarithm. Oh, let us write x squared. Logarithm z bar. So it can be written as 4 times dz bar acting on logarithm z plus logarithm of z bar. And what does it equal to, and why? If z is different from 0. So the question of about 0 is a separate question. Hmm? Who? What? What do you have in the differential? Hmm? Hmm? Hmm. So is there still some question, or it's clear? So is it fine, or are there some questions? But yeah, I actually asked a question about this function. So why doesn't this operator act by zero? What is the simple explanation? Oh, hmm? Oh, the explanation is that a dz bar kills the logarithm of z uh, because it does not depend on z bar. It is a homomorphic function, and it is an anti-homomorphic derivative. And dz kills the logarithm of z bar, so we can permute this derivatives to act on the second term. And that's all. So, so oh, for z different from 0. So it is some homomorphic function and anti-homomorphic. And it's actually literally the same phenomenon that we had for the wave equation. In that case, we had uh, psi equals x plus t, eta equals to x minus t, and we had an equation d psi d eta acting on f of psi plus g of eta equals to 0. It was for the wave equation. Right? So the difference with this 2D Laplace equation and the wave equation is this sign between second derivatives. So for the wave equation, we could write something like a squared dt squared minus dx squared as a product of two real derivatives, dt minus dx and dt plus dx. And for this Poisson equation of Laplace equation, we need to write I to combine this homomorphic and anti-homomorphic functions. So actually, this function of functions of x plus t and x minus t, which are also called coordinates, were direct analogs of homomorphic and anti-homomorphic functions. But the difference is that in that case everything was real and there were no restrictions, and so they could be just arbitrary functions. And in this complex case, we can ask, for example, for real solutions of this Laplace equation. So there will be some relation between homomorphic and anti-homomorphic function. And also we have a much smaller number of homomorphic and anti-homomorphic functions in some domain. Then the number of functions of psi and eta. So it looks almost the same, but globally it is a different situation. So is it fine? Is it clear? Hmm? Hmm? Sorry, one more. I wanted to ask, are you going to attend the next times or not? Ah, I see. Oh, because so did everyone give me your emails? Because if you want to attend or you want to receive some problems, so, do. So, so. Ah, mhm. Okay, okay. Mm, mm, mm. Sorry. So the question was about order, right? Mm. Mhm. Mhm. But logarithm of x to power a is a times a logarithm of x. So the same. Just wanted to write it this way to avoid writing this one halves and so on. So are there any questions? So. And by the way, so this way we obtain the green function, but this also suggests a way to write some solutions of a homogeneous equation. For example, in some domain, we can just take a homomorphic function and its complex conjugate, and it will satisfy a homogeneous equation, precisely as for the wave equation, and we will use it later. So the only difference between homomorphic function and this logarithm is that the logarithm has a singularity at 0, or you can shift it to any other point. So it has singularity there, and so it solves this equation with some delta function on the right hand side. And we still need to check that it is a real delta function, right? So is it fine or? Okay, so now let us check what happens around 0. So uh, let us just take this equation and integrate it over some domain. For example, over the domain, absolute value of x is less than some r. D2x Laplacian of g, it will be equal to 1 because we have this delta function on the right hand side. Uh, we can integrate it by parts to reduce to the integral over this circle. So, namely, we can write it as a d2x radial derivative. Oh, sorry. Integral over dn over over the boundary times gradient of g, and this is the integral over absolute value of x equals to r. So dn is this vector of of size n times delta L. Well, this theorem has some name, maybe Stokes theorem, but if you don't use it, you can just compute it in coordinates, just integrate everything by parts over this domain. So it is on this integral, and oh, let us suppose that we don't know that it equals to 1 and we want to compute this. So now we substitute this green function and compute its gradient. It will be this integral over dn, and gradient of logarithm is a vector directed um, in parallel to x with a length equal to 1 over x. So it will be this. So you can write it as a integral in dl. And I also forgot this prefactor 1 over 2 pi. dl, so absolute value of x equals to r, 1 over 2 pi x. And now we see that it is constant. It equals to 1 over r. And integral of dl equals to 2 pi r. So it is 2 pi r over 2 pi r. So it really equals to 1. So we checked that this integral of the green function equals to 1, and we also checked that Laplacian of it is 0 in all points except 0. So we proved this. So is it fine? Okay, so maybe it is all what I wanted to say about this about this green function. And I want to compute the green function of one more equation. So so far we know the green function of 1 plus 1 dimensional wave equation, and now I want to do this for 3 plus 1. In the sense for the wave equation that we have in our usual space. And then we will do the same trick to compute gain function for 2 plus 1. Because in principle it is some other integral which should be computed, but we can simplify this problem. So basically, the idea is that we find these gain functions of all equations of our interest, and then we'll apply them for some problems. We'll study something more specific, which includes, for example, boundary values or some initial values for different equations. So next topic is green function. 3 plus 1 wave equation. So this equation is d t t minus well, let me write it dt squared minus dx squared minus dy squared minus dz squared u and this vector xyz will be denoted by r. R is x, y, z. So and it will be delta of t, delta of r. Working on the gain function. So here we cannot use such kind of tricks because we did not solve any equations that has a different signs here. We only know how to solve this Poisson equation. But we see that even in this case, as a solution of equation with the minus sign and solution of this equation with plus sign are very different. One solution is some logarithm of z plus logarithm of z bar. Another solution is some theta function of x plus t, theta function of x minus t. So in principle, if we try to mimic one solution from another one and think about this as some analytic continuation in x to this z bar, probably we can get something, but I don't know any explicit way to do this without knowing the answer. The main point is that usually if we change some signs in the metric, we should do this computations from the beginning, and the answer depends on the signs. So it is something essential. And the answer can only be similar. They do not literally coincide. Okay, so we have this equation, and I propose to solve it precisely in the same way as we solved 1 plus 1 wave equation. Namely, let us take the Fourier transform of it. So let us write that this green function of t and x is in the Fourier transform of d omega dk over 2 pi in the power 4 over the whole space. E to minus I omega t plus I kx. So we are computing the E inverse Fourier transform of the green function. And who knows what should be written here? Like what is the Fourier transform of the green function of this equation? Just imagine that you take this formula with something in the denominator, act with this differential operator here. It gives something, and then you need to get the integral which represents this multidimensional delta function. So what should we write in the denominator? So if you write like this, if you don't write anything, it will be the delta function, because it's a product of identical integral in all these variables. Mm-hmm. Plus, yes, thanks, yes, like this. And now we can repeat the first part of the computation, which we did for 1 plus 1 case. Namely, you can compute this integral in omega. So again, we need to choose the contour in some way. So here we have omega plane, and this function has poles at minus absolute value of k and plus absolute value of k. And again, we want this integral to vanish when t is less than 0. I actually don't remember the answer, like in which half plane to close this contour, but it is easy to reconstruct. So it's this omega plane, and so here we want to draw a picture for negative t, and here we draw a picture for positive t. So t greater than 0. So for negative t, this contour can be closed in the upper half plane, right? Because no. So no, it's correct in the upper half plane, because negative t times minus I gives I, and the imaginary omega gives minus 1. So this contour can be closed like this. So, right. Oh yes, like this. And we want this function to be 0 in this domain. So for negative t. So this contour should be deformed in this way. So now if we compute it for positive t, then this contour can be closed in the lower half plane, and we have this sum of residues, right? So, then I can erase this. So let us write this again. So we have this expansion in the denominator. I wrote it to compute residues easily. So, so, so it is decay over 2 pi cubed, and the integrals in this residues goes in the clockwise direction. So we should multiply by minus 2 pi I. There is also this minus 1 coming from the denominator. and there is a sum of two terms. One is for this residue, so we basically erase this term and write only this one. So substitute omega equals to absolute value of k everywhere. So it will be e2 minus I absolute value of k t plus I kx divided by 2 absolute value of k's. So it's the first term. Another term comes from this residue. So now omega is equal to minus absolute value of k, and this will give the same denominator but with the opposite sign. So it will be minus e to the, oh, sorry, I absolute value of k t plus I kx over 2 absolute value of k. So are there any questions about this? So just the same computation as we did in 1+1 case. The difference is that here we have absolute value of k, and here we have scalar product of k with x. And that's all. Okay, so let us and also when we compute these values, we need to insert Heaviside theta, because this integral vanishes for negative t. So and it was 1 over 2 pi that came from that integral. So in total it is I times the integral of dk over 2 pi cubed over R3 of this function to absolute value of k e2 minus I k t plus I k x minus the same function with opposite sign. So it's some integral over three-dimensional space. And do you have any ideas how to compute something like this? So, in the cases where we had some rotational symmetry, we could, well, for example, here we could try to reduce something to Gaussian integrals, but here we see that we already lost this symmetry, because there is some parameter of this integral, namely the vector x. So there is some specified, there is some special direction. So it's not rotationally invariant. Let me check the recording. I just forgot it. Oh, thank you. This one. Oh, so idea here is the following. So this is the integral in this k space. So we have kx, ky, and k and kz. Uh, and the idea is to switch to spherical coordinates. These coordinates look in the following way. So there is some angle phi, which is measured from the x-axis. So we first move in this xy plane and fix a projection on this line. And so projection of our point in this three-dimensional space should lie on this line. So it doesn't look like projection. Projection should lie on this line. So it is one angle, and another angle is this one. It is measured from z-axis. This is angle theta. It's another coordinate. And third coordinate is just the distance to the origin, r. So k, absolute value of k. Or maybe let me denote it just by k. So, and can you write the formulas for these three coordinates, kx, ky, and kz, in terms of k, theta, and phi? So, kx equals ky equals kz equals. Hmm? Yes. So. Mhm. Hmm? 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 No, sine? No. But when theta equals to 0, they are collinear. So this function should equal to 1. Right? So it's not sine. Cosine? Okay. Yes. Cosine of theta is fine. Mhm. Yes. And, mhm. Yes. And here, so it's easy to check that some of the squares is actually in K. And do you know what happens with the volume element? So originally we have a dkx, dky, dkz. So what happens in this spherical coordinates? Mm-hmm. 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 dk, d theta, d phi. Right. So, does everyone know this formula? Uh, okay, good. Uh, hmm? So, oh, if someone never computed this, it is just a determinant uh, of kx, ky, kz over d k theta phi. On this product is on this one. So it can be just computed in mathematical manually. Okay, so perfect. The only question is how to choose this axis of this spherical coordinate system. But it is obvious because we have one vector x which is directed somewhere, and nothing else. This coordinate system has a symmetry, or some nice symmetry of rotations around this z-axis. So we just say that z-axis coincides with the direction of this x. So x x equals to z-axis. Oh, sorry. So what happened? So what happened with this integral? So, so we have this k squared sine of theta d theta d phi dk. So this is 2k. And by the way, what are the intervals for these angles? For this k, okay, k from 0 to infinity, theta from 0 to pi, and phi. Thanks. Okay, so what happens with the integral, with the integrand? So, so here it's absolute value of k, so it is just k. So it is e to minus I kt. Now what happens with ikx? Hmm? Cosine theta. Yes, thanks. So, and here it is ik t plus the same ik absolute value of x. Oh, I wrote x actually. Well, let it be. I wanted to use notation r, but it doesn't matter. Ik absolute value of x. Times cosine theta. So separate this from everything else. So now let us note that we can actually compute, so we can immediately compute this phi integral. It is just 2 pi. But we can also compute this theta integral. So it is I ph of t integral of k squared dk over 2 pi squared. I just integrated in d phi because nothing depends on phi. And now to compute this integral in theta, let us introduce the new variable cosine of theta. Let us write it as okay. So there is this prefactor. So there is e to minus I k t minus e to plus I k t over 2k. And here we have integral in d cosine of theta e to to I k. Let us use use notation r for absolute value of x. So let us call this r. So it will be ikr times cosine of theta. So d cosine of theta e to the ikr cosine of theta. So just on the integral of the exponential, and it can be computed. Hmm? There. Uh, yes, thank you. Yes. Uh, Thanks. So, and it's integral from, well, integral for in theta is in this range. Well, probably we can also write it here. So this integral, it is just the exponential of ikr cosine theta divided by ikr. And we need to compute a change of this function from 0 to pi. So let us maybe collect some signs here. Maybe let us combine these two signs. I theta h of t, k squared dk, pi squared. And here the upper value of this function is e to the minus ikr. A lower value is e to the plus ikr divided by ikr. Okay. Hmm? So I combine this minus with this exponential. Yes. So and now what happens? Now we can cancel this case in the denominators. This one, uh, this one, this one, and this k squared. And well, in principle, we can combine some signs here, but it's better to notice that we have two uh, two anti-symmetric functions. So their product is some symmetric function, and this integral in k goes from 0 to plus infinity, because spherical coordinates are defined in this way. And it is, of course, nice to extend this integral to the whole line. And so let us do this. We can also cancel this I. So it will be that heaviside 1 over 2 pi squared 1/4, because it was 1/2, and we extended the integral from minus to plus infinity. Minus infinity to plus infinity. Dk e to the ikt minus e to the minus ikt e to the minus ikr minus e to the plus ikr. So the question, I also missed this r, so it should be here. So, so the question is how to compute this integral. Like if we open all these brackets and we integrate each term, what will we get? So if you open these brackets, you will get some exponentials of the form e to the iek times something. And there will be all four combinations: x plus t, x minus t, minus x plus t, minus x minus t. Right? So what is the value of this integral? Integral from minus infinity to plus infinity, d k e to the I k times some a. What does it equal to? Yes, it was a factor to pi delta of a. Right. So what happens if we apply this knowledge to this integral? T minus r. Yes, we have this term. And what else? Plus? Oh, oh my. No, if it is t plus r, then it will be with a minus sign, because it works this way. Yes, and what else? So in the meantime, let me write on this part of. Okay, so what else? Because there are four terms if you open all these brackets. Mm-hmm. Mm-hmm. Yes. Thanks. Yes. But So there is this formula, but now the question is, can we drop some of these delta functions? Is it true that in our setting, some of them, arguments of some of them, never become zero? Yes. Yes. Mhm. But it's correct, but it is as a next question. And the first question is it true that some of these delta functions can be put equal to zero because they hmm? Yes, they are equal. But the point is that they also never appear in the answer because theta is always positive because of this theta heavy side, and r is positive because it is one of the spherical coordinates. So, so hmm? Yes, we can remove this and this. Yes. So. And it's correct that this delta is symmetric, so these contributions are equal. So we get a very nice formula. We'll also cancel this to pi. Uh, uh, Very nice formula. Theta heavy side of t over 4 pi r. Delta t minus r. So this is very similar to a one-dimensional problem, with the only difference that in that problem we had some theta function. And now, the first question is about consistency. So we already know this green function for uh, for the Poisson equation. And probably I've already erased it for the three-dimensional case. And so, do you remember the formula, at least schematically? So, so G Laplacian for d equals to 3 equals to minus 1 over 4 pi r, right? And I'm saying that this is consistent with our answer for the wave equation, because this wave equation contains second time derivative. So if you consider the right hand side, which is time independent, then its gain function, so its solution will be solution of Laplace equation. Right? So so if I compute this integral from minus infinity to plus infinity in dt, theta h of t over 2 pi of 4 pi r delta of t minus r. So what will it equal to? Hmm. 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 But r is always positive. It is the absolute value of x. It is the distance from the origin. So, so yes, it is true that we can write theta heavy side of r over 4 pi r, but r is always positive. So yes, so it's 1 over 4 pi r. So it is consistent with this formula. It's precisely this. The only difference is that here Laplacian appeared with the minus sign because we write a wave equation in this form. So. mm. So we said that, of course, it should be like this, but here it's a kind of independent verification that we did everything right. That this grand function it can be appeared by this reduction both from the heat equation and from 3 plus 1 dimensional wave equation. Mm. So. And because it's for equation out of x with plus sign in front of Laplacian, and here it appears with minus sign. So it was the same for the heat equation. Hmm. Maybe it's actually better just to put minus here, but I don't know. So, and now let us say something about interpretation of this green function. So, or if you have some delta function, it is always nice to do some computation where it disappears, where it kills some integral. And so, namely, let us just write the definition of the grand function in the sense that it is a function that encodes a solution of some equation with the right hand side. So we have this d t squared minus dx minus Laplacian u equals to f of t and x, u of t and x. So u of t and x is equal to the integral in d t prime dx prime and let me write this. Let me use this formula now. So it will be theta heavy side of t minus t prime divided by 2 pi 4 pi. So the value of r minus r prime delta of t minus t prime minus absolute value of r minus r prime f of t prime r prime. So we integrate this in t prime, and we have oh sorry, maybe let me write x. Sorry, x minus x prime. it's kind of synonym. So it's complicated to compute x integral because coordinates components of this x enter the delta function in some trivial way. But for t prime, for example, it is easy because it appears as a separate summand in this delta function. So when you compute integral into prime, it just puts t prime equal to t minus this distance. So, mm, so we have the integral d dx theta heavy side of uh, x minus x prime, which is of course 1, because it is always positive, over 4 pi x minus x prime. And so here we had t prime, and we should substitute it equal to this difference, f of t minus this distance, x minus x prime, x prime. So it is called retarded potential because to compute the influence of this right hand side on a function u at time t, we need to take this function f and the time that equals to t minus the time needed for a signal to travel from point x prime to point x. So, so there is some, or we can interpret it in the other way. So we can imagine that there is some point x, and there is some point x prime, which emits some signal, which propagates in the form of spherical waves with constant shape and constant speed. So in a sense that the a function which will be measured at point x in the same as a function at point x prime divided by distance between these points and also shifted in time. So, for example, let us consider a delta-like source at the origin. So this f of t prime x prime equals to some phi of t prime delta of x prime. So in this case, so what will be the value of u at t and x? So it will be this integral over dx 1 over 4 pi x minus x prime phi of t minus x minus x prime and delta of x prime. I hope I can compute this integral. What will we get? So the integral is over x prime. Hmm? Mm-hmm. Mm-hmm. Thanks. So, and it is very similar to one-dimensional case, with the only difference that we have this 1 over x prefactor. Because in this case we have spherical waves, and since they're spherical, their amplitude decays with distance. So there should be a picture like this. So we have this spherical wave. So there is this 1 over x. No, I can't draw 1 over x. Sorry. Some 1 over x. So if f, so this will be, this will be u, and this will be x at some moment t. And this picture is drawn for phi, which is just a periodic positive. So this is phi x. So phi is something like this. So, and here we again see this effect of retarded potential in the sense that to compute the value of u at some time t, we need to know the value of phi, the value of this source at time t minus distance to this source. And so, and one remark, so we will discuss it in the next time, but the remark is that it is actually a miracle, and it's an effect of odd dimensional space. If you go to the even dimensional space, this green function will not have this dependence in a sense to know the value of u at some moment of time t, we will need to know values of phi in all previous times. So in all previous times, which in principle can affect this point. So here will be not a delta function, but some kind of theta function of t minus yes, of r minus t maybe, or no t minus r. So it will mean that this wave front, it will mean that this spherical waves in spaces of even dimension will have only the first front, but not the second. Like they will have forward front, but not the rear front. So in 3D, we have picture like this. So if you uh, insert some delta functional source, it will be this peak which travels with speed 1. And in 2D, the picture will be like this. There will be sharp forward front, but then it will decay by some power low. And it means that if we lived in, for example, two-dimensional space, it would be hard to communicate with voice, because any sound would produce this decay and echo. So, and also, if you compare this answer with the answer for the Poisson equation, where it was just 1 over r to some power, you see this a huge difference between delta function and 1 over r. So in some sense, they can be related, because we see that delta function is a kind of friend of a principal value of 1 over x, but only in this sense. They cannot be obtained from another function by some well-defined procedure. So, and also it's kind of the simplest answer for these gain functions, because if you go, for example, 5-dimensional space, it will be some derivative of the delta function, and it's always like this, but it is much less trivial to compute, and we will not think about this. Okay, so that's all. Do you have any questions about this? So probably I'll add some problems about this, maybe about something else today or tomorrow. Okay, thanks for your attention. See you tomorrow.